You are watching video number 6 for Mr. Sweeney's AP Physics C class, and in this video we're going to discuss conservation of energy and the relationship between work and potential energy. And we're going to start by discussing conservation of energy. This should be a familiar topic. We've alluded to it so far. Conservation of energy states that the total mechanical energy of a system is the sum of its kinetic and potential energies. That is, the mechanical energy is equal to kinetic plus potential energies. And for the conservation part, it states that in an isolated system, and what I mean by isolated system is that a system where no external forces are acting upon it. The forces would just be between components of the system or come from internal energies already existing within the system. So nothing outside of the objects that are part of the problem are acting on it. So in this isolated system, where only conservative forces are acting, that means no friction, the total mechanical energy of the system will remain constant. So if you have a system where no friction is present and nothing outside the system is acting, the energy that's there will remain there at the end. And we represent this by saying the energy of the mechanical system, that's equal to the change in kinetic plus the change in potential energies, and that's equal to 0. So the change in energy over the system will always equal 0. Now, if you're looking at the change in kinetic and the change in potential energies added together to equal 0, that means if there's any increase in kinetic energy, there must be a corresponding decrease in potential energy, and vice versa. And this allows us to identify this relationship, that the change in kinetic energy is equal to the negative change in potential energies. And we see this all the time. If you take the simple example of a falling object, if I drop an object from a height, its potential gravitational energy will decrease as it falls, and as it falls there will be a corresponding increase in its kinetic energy. So we see this where kinetic energy and potential energies, as one increases the other decreases. The flip side is also the same. If I were to throw a ball upwards, it would leave my hand with a particular kinetic energy. As it rose, as it increased its height, the kinetic energy would decrease, but the potential energy would increase. So as one increases, the other decreases. Conservation of energy says that energy will stay constant, but it also leads to this idea that kinetic energy and potential energy, as one will increase, the other will decrease. We can also look at conservation of energy with the idea of something outside of the system working on it. So I said when I defined conservation of energy that an isolated system, a system where no forces are acting on it from some external force acting on the system. But what about if there is an external force acting on the system? And this is not a very uncommon idea. You know, things are pushed back and forth by external forces. So what happens when an external force pushes on a system? Well, the work done by that external force, remember that work is equal to force times displacement, or the integral of force with respect to displacement if the force is variable, that work will increase or change the energy of the system. And we say that work done on the system by an external force changes the energy of the system. That is, work equals change in energy. Now this is for a system where work is done by an external force, but there's no friction. So the other aspect of conservation of energy that I discussed had to do with a frictionless environment. So let's talk about what happens if friction is present. If it's present, the work being done to the system, some of the energy will be transferred from the system into thermal energy. So we see that like if we rub our hands together, there's friction between our hands heat up. friction always leads, the loss in energy due to friction always leads to an increase in thermal energy. We can look at this work being done to the system as work equals the change in mechanical energy plus whatever thermal energy is being taken out of the system due to friction. So if you work on a system, some of it will go to mechanical, some of it will go to thermal energy. Unless it's frictionless, then all the work will go to mechanical energy. These ideas, the thought that conservation of energy says that the energy of an isolated system is constant, we can hold that position. We can look at how it would be affected if we had an external force acting on it. And we can also take into account if there's any friction or non-conservative forces. And when I say friction, that would include anything such as air drag as well, air drag or a drag force as well. So let's take this one step further and take a look at this relationship of work to energy by examining closer this concept of work and potential energy. Now, when we first identified work and defined it, we defined work as force times displacement, or the integral of force times change in position if we had a non-constant force. And we're going to start this discussion with this idea: work equals force times displacement. Now, we identified work as a positive value. Remember, it is a scalar value. It doesn't have a direction. Work doesn't. But we had a signing convention, meaning that if the force and the displacement were pointing in the same direction, work was positive. If the force and the displacement were pointing in opposite directions, work was negative. Now, when you talk about potential energies are always going to be stemming from conservative forces. Gravitational force is a conservative force. Elastic energy is a conservative force. Now, when we work against gravity by raising something, for example, as we raise an object, the force being placed on it from gravity is pointing in the downwards direction towards the center of the Earth, but the displacement of the object is going upwards. So when we work against gravity, the work done by gravity in raising an object is negative because the displacement and the force are not pointing in the same directions. And we see that when work is done against a conservative force, such as elastic or gravitational force, the conservation force acts in the opposite direction of the displacement. This means the work is negative. Now, the energy is increased, potential energy is increased, but the work itself is negative. So we have this relationship that the change in potential energy is equal to the negative magnitude of the work. Now remember that both of these are scalar values, and we're working with signing conventions. So the negative and the positive, by definition, is given here in its most proper form. But the most important idea that I'm talking about here is that when you do work against some sort of source of potential energy, gravity or elastic, that the magnitude of the work is equal to the magnitude of the potential energy gained. And what we're really working with this equation is just looking at the signing conventions. Force gravitational would be pointing opposite in the way when you're increasing the potential energy. Same thing with elastic. If you push against a spring, the force of the spring would be pushing against in the opposite direction that the force is being applied to compress it. Now we're going to use this idea that the change in potential energy is equal to negative work to try to gain some understanding of how this potential energy is going to be related to the force being applied here. Now we have these two equations. We have the potential energy, or the change in potential energy, is equal to the negative work. And we also have this idea that work is equal to the integral of force times displacement, which is really just saying work equals force times displacement, and the integral is just referring to the fact that sometimes this force is non-constant. In this idea, if both the change in potential energy is equal to work, and the work is equal to force times displacement for conservative forces, we can write this relationship. that the change in potential energy is equal to the negative integral of force times displacement. And we identify this by saying the change in potential energy comes from one-dimensional conservative force is equal to the negative of the integral of the force with respect to position. Now, this idea that if you integrate force, you get the change in energy, can be also represented as a derivative. If you take that change, that integral of force, and you take the derivative of it, they're inverse operations. You'll be left with force. But you'd have to take the derivative of both sides. So you could represent that previous equation where you said that the change in energy, potential energy, is equal to the integral of force dx, and say that same relationship in reverse would be that the force function is equal to the negative derivative of potential energy. So we have two ways of stating this relationship between potential energy and force. We could say that potential energy is equal to the integral of force, or we could say that force is the derivative of potential energy. The consequences of that relationship are best shown in the potential energy curves. And we see these on AP exams, we see them in homework problems. They're a good way of showing how potential energy affects different systems. Now, the potential energy curve itself shows how the potential energy of a system changes with the position of an object within the system itself. Now, this curve for potential energy only represents systems with conservative forces acting on them. This is important because potential energy itself only stems from conservative forces such as elastic and gravitational, which are conservative forces. And here I've shown you an example of what a potential energy curve would look like. On the y-axis we have potential energy, and on the x-axis we have position. So let's take a look at that relationship we just established in the previous section. It says that the force is equal to the derivative, or the negative derivative, of potential energy. What this means is that the slope, because remember the derivative is equivalent to the change in position at a point, that's the slope. The slope of the potential energy curve at any point is the negative of the force acting on a system at that point. So if you're looking at the slope, if the potential energy curve here has a negative slope, that means that along this first line from xo to x1, because that slope is negative, there's a positive force acting on the system. It's doing positive work. From x1 to x2, the slope is positive. Because it has a positive slope, that means in this scenario, between those two positions, the force acting on it is negative, meaning it's doing negative work on our system. So here we can interpret the slope of our graph to represent the forces acting on there. Now, when the kinetic energy at a point is given, and this is very common, you see this in AP problems very often, that they'll give you a potential energy curve, they'll identify what the kinetic energy is at a particular point. Remember that due to conservation of energy, especially when we're looking at conservative forces, that if you know the kinetic energy and the potential energy at any point, you know at that juncture the total energy of the system. So if they give you the kinetic energy at some point, doesn't matter what point it is, you can just add that to the potential energy at that point to find what the total energy of the system is. Now this total energy of the system will remain constant throughout every point, so when they give you that kinetic energy at one point, they're really giving you a method for finding the total energy of that point. But that total energy at that point, that applies to every point in our system. So once we know that total energy, the kinetic energy at any point in the system can be determined through conservation of energy. Remember that conservation of energy says that the total energy in our system is equal to the kinetic plus the potential energies. So if we know it at one point, we know it at all points. And we can find that kinetic energy through this simple relationship. It says that the kinetic energy is equal to energy of our system minus the potential energy. This is just a rearrangement of E equals K plus U. We've subtracted U from both sides. It says kinetic energy now is equal to energy minus potential energy. There's a couple of particular points, and we see these on AP exams, that we have to understand in our potential energy curves. The first one that I'm going to talk about is a turning point. A turning point is a point at which the kinetic energy is zero, meaning that as you move from one position to another, if the kinetic energy ever becomes zero, that object, as it's moving, will stop. If it has no kinetic energy, it cannot be moving. Now, if you're going to stop in a potential energy system, the moment that you come to a stop, because you would still have some potential energy remaining in the system, that potential energy will convert itself back into kinetic energy, meaning that the moment that kinetic energy goes to zero, that object will stop and turn around. And there's a really simple example of this that we see all the time, and that is a pendulum. When a pendulum is moving, the moment that it reaches its highest point, the bob will come to a stop momentarily before turning around. Oftentimes we see situations where an object is caught in a particular position because as it moves from one spot to another, its kinetic energy shifts with potential energy. One increases, the other decreases. As soon as the kinetic energy goes to zero, the potential energy then will hit its maximum point, and the object will turn around, and it'll go back to more kinetic energy, and potential energy will decrease. We see this with the constant repetitive motion of a pendulum. At its highest points, those are the turning points of the pendulum. They stop, turn around, go the other direction. There's one other points that are of note in our potential energy curves, and those are equilibrium points. Remember that the slope of the potential energy curve is equal to the magnitude of the force. F equals the negative derivative of potential energy with respect to position. Now, if the slope is represented of force, when the slope is zero, because force is equal to the slope, that means the net force on the object when the slope is zero, meaning that it's at equilibrium. Remember, equilibrium is zero net force. So whenever you have a zero slope position on your graph, that means that at that point in the graph, equilibrium has been achieved. Now, sometimes we will have both equilibrium being achieved and kinetic energy being zero. This would be an object that's at rest, that's in equilibrium. If potential energy, if the slope of the potential energy curve is non-zero, when the kinetic energy is zero, then the object will continue moving at that point. That would be sort of like an example of the pendulum. Kinetic energy at zero, but it's not at equilibrium, it's going to keep moving. But an equilibrium and a zero kinetic energy would be, say, like a marble that's sitting on top of a horizontal table. Kinetic energy zero, potential energy for that position would be zero as well, or would have a zero slope, meaning that it has zero net force. And this concludes our notes on energy.